Since ancient times, Mars has held a special place in the human imagination. Astronomers once looked to the red planet with hopes of finding life, and today, that obsession has taken on a futuristic edge. We dream of Martian cities, self-sustaining colonies, and even the possibility of starting a new civilization in its desert landscapes. Elon Musk, for instance, has already laid out bold plans. He wants to send astronauts there around 2030 and establish the first permanent settlements by the mid-2050s. On the other side of the world, the United Arab Emirates are aiming even higher, with a project to build a city of 600,000 inhabitants on Mars by the year 2117. And astrobiologist Lewis Darnell, a professor at the University of Westminster, believes it might take 50 to 100 years before we see a significant population living there autonomously. But here's where harsh reality kicks in. Turning that dream into something real takes much more than imagination. Sending probes and robots to explore Mars is one thing. Sending humans there to live permanently is a completely different story. The gap between exploration and colonization is enormous, almost insurmountable with current technology. We're talking about a planet with no oxygen, freezing temperatures, dangerous radiation, and a severe lack of water and food. Any project that imagines hundreds or thousands of people living there must first deal with these colossal obstacles. So if you've been dreaming of growing Martian potatoes like in the movie The Martian, it might be time to admit that, for now, that's more fiction than fact. Before we go any further, it's important to say that this video doesn't aim to downplay the incredible progress we've already made in space exploration. Quite the opposite. The fascination with this topic is exactly what motivated me to create this channel. But with our current technology and resources, it's unlikely we'll see humans settling on the red planet anytime soon. Still, let's use our imagination. Let's take a hypothetical trip to Mars using the technology we have today and try to understand, step by step, the massive challenges involved in such a mission. The goal here is to show why, no matter how much we want it, trying to colonize Mars right now would be, at the very least, disastrous. To begin with, we face the first major hurdle: the journey itself. Getting to Mars would take anywhere from 6 to 9 months, just one way. A full mission, including the stay and return, could last more than 2 years. This means the spacecraft would need to be entirely self-sufficient for extended periods, supporting human life with no direct help from Earth. And even worse, outside Earth's magnetic field, astronauts would be exposed to intense cosmic radiation and highly energetic solar particles. This significantly increases the risks of developing cancer and other serious health problems. And that's not all. Spending so much time in microgravity also has devastating effects on the human body. Bones lose density, muscles weaken, the heart undergoes changes, and the immune system becomes dysregulated. And as if that weren't enough, there's also the psychological impact of extreme isolation. Months confined in a small space, with no direct contact with Earth, far from natural light and familiar scenery. Of course, radiation is a particularly critical problem, but that doesn't mean we're doing nothing about it. Research is already underway to develop passive radiation shields, such as hydrogen-rich materials, and even more ambitious ideas like artificial magnetic fields. But all of this is still in early development. One idea being studied involves filling parts of the spacecraft with bags of radiation-absorbing materials to protect the astronauts. But this raises practical questions. How can astronauts maintain a regular exercise routine, crucial for preventing muscle atrophy, if the usable space is taken up by these bags? How can freedom of movement be ensured inside the ship without compromising radiation safety? And worst of all, even with these solutions, the risk isn't completely eliminated. The first astronauts might already arrive on Mars with health issues. Let's imagine, then, that we overcome that barrier. The spacecraft finally enters Mars's orbit. Now we face a new challenge, perhaps one of the most dangerous parts of the entire mission: the landing. This moment is so critical it's earned a sinister nickname among NASA engineers: the 7 minutes of terror. That's the time it takes for a spacecraft to pass through the Martian atmosphere and reach the surface. Just enough time for any failure to lead to disaster. The problem is that Mars's atmosphere is incredibly thin, only about 1% the density of Earth's atmosphere. This means it offers little resistance and almost no help in slowing the spacecraft down. Conventional parachutes are nearly useless in that environment. The spacecraft arrives at about 19,000 kilometers per hour and needs to decelerate to zero in just a few minutes. Yes, NASA has successfully landed rovers on Mars, but those were small, unmanned, lightweight vehicles, not even close to the size and weight of a spacecraft carrying humans and tons of equipment. To deal with this, engineers propose a mix of technologies: heat shields, supersonic parachutes, retro propulsion, and AI systems to help with landing precision. All of these have been tested with probes, but never with crewed ships. And since time is ticking, the first real test may happen during a mission with people on board. A risky bet, to say the least. But let's say we survive that critical moment. We land on Martian soil without exploding on impact. The next step is setting up camp. And it won't take long for the astronauts to realize that Mars is far from welcoming. Temperatures can drop to minus 125 degrees Celsius at night, the atmospheric pressure is nearly zero, and there's no breathable oxygen. Any failure in a spacesuit can be fatal in a matter of seconds. So the top priority is to build safe and functional shelters. Today, the most viable housing options include three possibilities: pressurized inflatable modules, underground habitats, and 3D printed structures using Martian soil. Each option has its pros and cons. Inflatable modules are lightweight and easy to transport but extremely vulnerable to punctures. Underground habitats offer natural protection against radiation, but require complex excavation and heavy machinery. Something unrealistic for an initial mission. As for 3D printing structures with Martian regolith, it's an interesting promise, but far from being tested on a real scale. So the first explorers will likely have to settle for fragile but practical inflatable modules. But shelter is just the beginning. The real challenge is securing the essential resources for survival: water, oxygen, and food. Bringing all of this from Earth would be logistically and financially unfeasible. Even with prior cargo missions, it would still be impossible to transport everything a crew needs for months or years. So the only way forward is to produce these resources locally. Extracting water, for example, could be done from underground ice already detected in certain regions of Mars. But melting and purifying this ice requires energy, time, and infrastructure. Another option is extracting moisture from the air, but Mars' atmosphere contains very little water, making this method extremely inefficient. One of the most promising experiments ever conducted on Mars to try producing oxygen was the MOXIE experiment, carried by the Perseverance mission. This small device successfully converted carbon dioxide from the Martian atmosphere into oxygen using solid oxide electrolysis. Sounds promising, right? And yes, it's an exciting advancement. However, MOXIE is still just a miniature prototype, capable of generating enough oxygen only to keep a small candle lit for a while. To support an entire crew, this output would need to be multiplied dozens or even hundreds of times. We're talking about a massive challenge of scale and efficiency. Now, when it comes to food, things get even more complicated. If you've watched the movie The Martian, you probably remember the scene where astronaut Mark Watney grows potatoes using his own waste as fertilizer. It sounds absurd at first, but it's actually based on real principles. He used hydrazine, a rocket propellant, to extract hydrogen, which he then combined with available oxygen to make water. All of this is chemically possible but also extremely dangerous. Hydrazine is volatile, corrosive, and can explode easily. Any mistake in the process could turn a small lab into a deadly trap. Even if the process works, it assumes there's already a base equipped with oxygen supplies. And there's an even bigger issue. Martian soil is extremely toxic. It contains high levels of perchlorates, chemical compounds that are poisonous to both humans and plants. To grow anything there, the soil would need to be washed or treated to neutralize those compounds using processes that require large amounts of water and advanced technologies. And as we've seen, water itself is already scarce and hard to get. On top of that, Martian soil is sterile. It lacks the organic matter we have on Earth, which is essential for growing food. It also contains traces of heavy metals, radioactive elements, and oxidizing compounds that pose serious health risks with prolonged exposure. Even worse, its particles are extremely fine, similar to lunar dust, and could cause lung diseases if inhaled regularly. Issues like silicosis, common among Earth's miners, could become a reality for Martian settlers. That's why experts believe that growing food on Mars will need to happen in hydroponic or aeroponic greenhouses. In these methods, plants grow in water, enriched with nutrients, or in controlled environments using nutrient mist, without direct contact with soil. The nutrients would need to be brought from Earth or synthesized locally, which requires detailed planning and abundant energy. In fact, it's likely that this same growing system would be used during the trip to Mars itself, ensuring a continuous and safe supply of fresh food. And the problem with Martian regolith goes beyond toxicity. Working with this material demands strict safety measures. Any operation involving excavation, construction, or mining must ensure that harmful particles don't enter the habitat or cling to the astronauts' suits. Efficient decontamination systems are mandatory, but again, they consume a lot of energy, a critical and limited resource on Mars. Speaking of energy, that brings us to another massive hurdle. Mars receives only about half the sunlight that reaches Earth, and what little it gets is often blocked by dust storms that can last for weeks and cover the entire planet. In an environment where everything depends on artificial life support, from water production to temperature control, a power failure could be catastrophic, literally a death sentence. The most promising alternative in this scenario would be nuclear reactors. Nuclear fusion, the ideal solution, is still in the experimental phase and far from being viable. Nuclear fission, currently used in Earth-based power plants, is functional and powerful, but it comes with huge risks. If something goes wrong with a reactor on Mars, there would be no way to evacuate the astronauts or contain the damage quickly. On a planet where everything depends on artificial systems and constant maintenance, any failure could be fatal. And there's more. To operate a reactor on Mars, we'd need to send nuclear material from Earth. That means launching rockets loaded with uranium or plutonium, something that's terrifying just to imagine. A single launch accident with a rocket carrying radioactive material exploding in Earth's atmosphere could have disastrous consequences. This situation demands not only advanced technology but flawless safety protocols, something we're still far from achieving. Beyond all these technical obstacles, there's one factor that's often overlooked but absolutely essential: the mental health of the astronauts. Spending years isolated in a hostile environment, far from family, with no nature, no fresh air, no freedom to walk outdoors, all of this can deeply affect a person's psychological state. Simulated missions on Earth, like NASA's HERA program, aim to study this impact, but they can't fully replicate the extreme experience of living on another planet. Confinement alone is already tough, but imagine facing an emergency without being able to communicate with Earth in real time. On Mars, communication delays can exceed 20 minutes. Any critical decision would need to be made locally without direct support. This demands highly reliable automation and extremely well-trained crews to handle any unforeseen situation. And this brings us to a crucial point. Many people have heard that a crewed mission to Mars would be a one-way trip. That idea gained popularity with projects like the now-defunct Mars 1, which promised to build permanent colonies with volunteers willing to never return. But today, this approach is no longer taken seriously by major space agencies. Both NASA and SpaceX are planning missions with guaranteed return. SpaceX's reusable Starship rocket was designed specifically for that, to go to Mars and come back using fuel produced on the red planet itself. On paper, this proposal is impressive. The idea is to use the abundant carbon dioxide in the Martian atmosphere and hydrogen, either brought from Earth or extracted locally, to produce methane and water through the Seperti reaction. The oxygen needed for combustion would be extracted with the help of electrolyzers like MOXIE. This way, the Starship's tanks could be refueled directly on Mars, enabling the return to Earth. But turning this theory into practice requires a level of logistical and technological precision that we haven't yet achieved. Return vehicles would need to be sent ahead of the crew's arrival, refueled, and thoroughly tested. Any failure in that process could lead to a forced stay, a scenario no space agency wants to face. With today's advancements, returning from Mars might be technically possible, but it's still logistically challenging. One-way missions, though simpler in theory, are ethically controversial and operationally risky. After all, if for any reason the return system fails, the crew would be forced to remain in a hostile environment with limited resources and no real chance of rescue. That's why every crewed mission to Mars must be designed to ensure complete self-sufficiency, both upon arrival and departure. And even with all the automation and artificial intelligence available, there's still a lot that AI can't handle. Creative problem-solving, real-time decision-making, improvising in the face of technical failures, these things still rely on human judgment. AI can certainly help analyze data, operate complex systems, and even predict failures, but it doesn't replace human discernment in unpredictable situations. And as we've seen, almost everything on Mars is unpredictable. Considering everything we've discussed, it might seem like colonizing Mars is a completely absurd idea, something straight out of science fiction and nothing more. But that's not what we're saying here. Humanity can, in fact, get there. It's just going to take much longer than people imagine. This video simply presents the facts, what we can do with today's technology and what still lies far beyond our reach. The truth is, throughout history, humans have always wanted to go further, always wanted to explore what's beyond the horizon, even when that meant facing death. Thousands of people have climbed Mount Everest, knowing the risks. Many died trying, and yet others kept climbing. We've gone to the poles of the planet, to frozen, inhospitable places where no one should live. And even in these extreme environments, we built temporary bases. This shows something fundamental about us. We have an insatiable curiosity, a drive to explore and conquer boundaries, even when they seem impossible to cross. In the 1960s and 70s, after the first trips to the moon, people thought Mars would be the next natural destination. Those predictions didn't come true, and that teaches us a valuable lesson. We must not confuse aspiration with reality. We need to dream, yes, but with our feet on the ground. If the human species manages to survive long enough, there's no doubt that one day we will colonize Mars. The question isn't if or how, but when. And for that when to arrive, we need to make sure our civilization survives here on Earth. Yes, it sounds like a cliché, but think about it. If we can't secure a decent and sustainable life on the only planet shaped by life, how can we possibly do it in a frozen, toxic desert millions of kilometers away? Colonizing Mars will require a gigantic technological leap, but before that, it will demand responsibility for our own world. We need to keep investing in science, in innovation, and above all, in sustainability. We must keep our civilizations alive, functional, and ready for the future. Space may be the next step, but it will only be possible if we continue to exist and evolve here on our blue planet. So, what do you think? Will humanity manage to become an interplanetary civilization? Or will we destroy our chances before we even try? Let me know in the comments. Let's talk about this idea together. If you enjoyed this analysis and haven't subscribed to the channel yet, now's the time. Leave a like and share this with your friend who also loves space. Thanks for watching, and see you in the next video.